One method that we can solve this problem is by choosing a point in the shaded area and subbing them into each one to see if it works. But another method that I've kind of been hiding from you guys, this only works in special cases like this, is, for example, here, if we have the y's by itself, then we can see that it's saying that the y value for this line has to be greater than 1 always. And this one, the y value has to be greater than this line. So that means the y values have to both, the shaded areas have to both be above both lines. So let's take a look at this. And here we see, yes, the shaded area is above here. And here if we go directly up and down, the shaded area is above, not below. So I can see, since it's both greater than, they're both up, then it's going to be greater than and greater than. So this problem is very similar to the one we just had on our quiz recently. In fact, I think it's almost exactly the same. So first thing we have to do is figure out, is this a growth or decay function? Then we can decide which way we want to go. So if we want something that's closest to the x-axis, we can look at that next. So first, since our growth factor of 2 is bigger than 1, it's going to be a growth function, since 2 is bigger than 1. So we know it's growth, so that'll take the shape of a right hand. So it looks something like this on top of the x-axis. So now, just from this, looking at this graph, we can see, do I want something further to the left or further to the right to see what's closest to the x-axis? And it's pretty obvious that the further left that I go, the closer it gets to the x-axis. So we want the point on the x-axis that's furthest to the left. So let's think about this. Which one's going to be furthest to the left? So that's the smallest number, and let's see what we got. So let's it's hard to compare these. We have to be able to do this some other way rather than just looking at the fractions. So maybe one way we can compare them is getting either common denominators, or we can put them as decimals. So I'm actually going to use the common denominators after kind of canceling things out. So for example, this one you might be able to see already, but this one's pretty big. This is also bigger than a half. You might be able to see that. This one's smaller than a half, and this is a half. So this is already the smallest one just by eliminating, by comparing it to 1/2, which one's bigger. But if you can't tell that answer, then let's actually get the decimals. So 1/2 as a decimal, we can just divide 1 divided by 2, which it goes in 0 times, so we put a decimal and we get 0.5. 3/5, if we do that, that's 3 divided by 5. 0, add the decimal, and it goes in 6 times, so 0.6. 3/7, well, let's try that one, 3 divided by 7. If I go in 0 times, we can add the decimal, it goes into here 4 times, so we get 0.4. And then 7 divided by 9. It goes in 0 times, so then it goes into here 7 times. And so we can see the smallest number still, which is furthest to the left, is again 0.4, which is C. When looking at problem number 7, what we need to try and figure out first that's easiest is looking at A and D, because these are just asking about their intercepts. To see if they have the same y-intercept or the same x-intercept is really easy because we just plug in zeros. So to find the same y-intercept, see if the y-intercepts, all we do is plug in 0 for x. To find the x-intercept, we just plug in 0 for y. So let's do that first. Let's work on A first. The other way we can do is cover it up, but it's hard to show that on a screen. But to find the same y-intercept, let's plug in 0 for x on the first one. And what do we get is negative 4y is equal to negative 8. And then if we divide by negative 4, we get y equals 2. Then I do the same thing on the other line, so this was line L. And let's do the same thing with line Q. And I'm going to get negative 2 times 0 again, minus 4y is equal to 3. And that cancels out, so I'm left with negative 4y is equal to 3. So y is equal to 3 over negative 4. So we can see right away that the y is not the same as this y-axis, so they don't, or y-intercept, so they don't have the same y-intercept. Then we do the same thing with the x-intercepts. This time we have to plug in 0 for y. So if I do that, I get negative 2x. 0 for y on this one is going to cancel it out. So we get mine equals negative 8, and x is equal to 4. If I do the same thing here, plug in 0 to y, it's going to cancel it out. And I get negative 2x minus 4y. Oops, not minus 4y, that's 0. That's going to cancel out. So we get negative 2x is equal to 3. So x is 3 over negative 2. So they're not the same either, so it's not this. So the only other option we have is either that the lines are parallel or they're perpendicular. And remember, the way we can tell the difference between those is if it's parallel, then they have to have the same slope. If they're perpendicular, the slopes are opposite reciprocals. So let's check if they're parallel or perpendicular. So what we do is we put the y's by itself, put it in slope-intercept form. So let's start with line L. So we get negative 2x minus 4y is equal to negative 8. And if I get y by itself, I can do this by adding 2 on both sides. 2x, I mean. And we get minus 4y is equal to 2x minus 8. And if I divide by negative 4, then we're going to get the number in front of the x is the slope. So 2 over negative 4 is going to reduce to a slope of negative 1/2. Now let's do the same thing for the other one. So I'll kind of separate this work out here. So if we do the same thing for the other one to see if it's parallel, then we can get the slope on that. And so let's see, line Q now. We're going to get negative 2x minus 4y is equal to 3. So let's get y by itself. So I'm going to add 2x. And I get minus 4y is equal to 2x plus 3. And then if I divide by negative 4, we can just look at the slope. That's the only part we're interested in. So 2 divided by negative 4, again, reduces to a slope of m equals negative 1/2. And we see, oh, those slopes are the same. So for both lines, so same slope means they're parallel. For problem 8, this is where we want to use the vertical line test, so to see if something's a function. So let's just start with the relation, the one that's given to us right in front of us. We just look, and if the line passes through our graph more than once, a vertical line, if it passes through it more than once, then it's not a function. And we can see, oh, it goes through there, and it goes through there. So that's 2 points. And 2 is more than 1. That's too many. So we know that the relation is not a function. So it's either going to be, let's see, this one has relation is not a function, and this one has relation not a function. So we can eliminate D and A. So the only other thing we got to look at now is the inverse. And the way we would do this on paper is we can either turn this sideways, right? So you can imagine the x becoming the y-axis and the y becoming the x-axis. Or we can just turn our line sideways and use a horizontal line. So if I just turn your head sideways and do this, we're going to see that, okay, if I cross through there, then we're going to see, let me actually erase the other line. If I cross this way now, oops, anywhere on here, we can see that everywhere we go is always crossing the graph only once. Once on this line, once on this line, once on this line. And so we see that, okay, since it only crosses once, it must be a function. Once is okay, more than once is not. So it is a function, which is C.